Hi, everyone. This is part 2 of my talk. And for this part, I'll be talking about the spectral to geometric correspondence, and starting with an example in Euclidean space, moving to compact hyperbolic three manifolds, and then talking about how that's used to prove my results on bias in holonomy. Okay, so I'm going to start with a very popular question, which is, can you hear the shape of a drum? So this question was posed by Mark Katz in 1966. And the mathematical version of this question is, do the frequencies at which a manifold vibrates determine the shape of the manifold? So in Euclidean space, the answer is no. So this example was given by Gordon, Webb, and Wolpert in 1999. And this was an example where the two manifolds, or maybe not manifolds, but these two spaces vibrate at the same frequency, but they are not isometric. They're not the same shape. Okay, so for compact hyperbolic three manifolds, the answer is also no. But the spectral information does determine a lot of information. So for example, it determines the lengths of closed geodesics. Okay, so we want to quantify this problem a little bit more. So in two-dimensional Euclidean space, we have our standard Laplacian. And eigenfunctions are functions that where the Laplacian on that function is equal to a constant multiple of the function. So that eigenvalue lambda is the frequency at which the space vibrates. Okay, so this question of can you hear the shape of a drum is really asking, do the eigenvalues of a manifold determine its shape? Okay, so sticking with Euclidean space for a little bit, we're starting off with the two torus. So what I mean by the two torus is really R2 and then modding out by an integer lattice. And so the eigenfunctions in that space are the functions e to the 2 pi I times nx plus my for any integers n and m. And if you want to do a fun exercise, it's very nice to compute the Laplacian of this and double check that it's a multiple of the original function and that the eigenvalues you get are negative 4 pi squared times n squared plus m squared. Okay, so we have this set of eigenfunctions, and it turns out that this forms an orthonormal set. So it spans the whole L2 space, and all of these functions are orthogonal and they're normalized to have norm 1. And so, okay, so what happens is that we have a Fourier series expansion, where if we have any sufficiently nice function on the torus, this can be written as an infinite linear combination of these special eigenfunctions. And this sum converges in the L2 sense. But if you add more conditions, like if you ask that f is smooth, then this will really converge in the traditional pointwise sense as well. Okay, so once we have our spectral expansion, or here our Fourier expansion, we also get this beautiful result called the Poisson summation formula, which says if we have any sufficiently nice function on R2, so for example, a smooth, rapidly decaying function on R2, we get this beautiful equality where we can sample the integers n and m either with the function g or with the Fourier transform of G. Okay, so this is a beautiful correspondence where we're sampling on one side with G, the other side with the Fourier transform. Okay, so I'm going to move on to hyperbolic 3 manifolds. And the reason that I started out with this Euclidean example is that this Poisson summation formula is actually an example of a trace formula. And the trace formula I want to talk about is Selberg's trace formula for hyperbolic 3 manifolds. Okay, so we also have a Laplacian in this hyperbolic space. And automorphic forms are these special functions that are eigenfunctions of the Laplacian. And if you are in a non-compact space, then you also have to satisfy some decay conditions going into the cusps. But we're just going to talk about compact here. So if we're in a compact hyperbolic 3 manifold, then there will be an orthonormal set of automorphic forms where any L2 function on our manifold has the spectral decomposition where it can be written as, again, an infinite linear combination of automorphic forms. Okay, and L2 just means square integrable, so it's not growing too much. Okay, so this is a version of the classical Selberg's trace formula for compact hyperbolic 3 manifolds. And what we have here is that we're sampling on one side the eigenvalues of the Laplacian, and then on the other side, we're sampling the lengths of closed geodesics. And this looks a little bit funny here, but this is some sort of Fourier inversion on the spectral parameter. Okay, so we have this relationship here between eigenvalues of the Laplacian and this geometric information about the lengths of closed geodesics. And I will also say that we write the eigenvalues as 1 minus nu squared, and then nu is called our spectral parameter. Okay, so the classical Selberg's trace formula results from this spectral decomposition of our L2 space of our manifold and relates eigenvalues to lengths of closed geodesics. However, I'm interested in studying the holonomy of closed geodesics. So I look at non-spherical trace formulas. So these result from the spectral decomposition of a larger space of the L2 space of G mod gamma, where G is the group PSL2C of the isometries of hyperbolic space. Okay, and when you look at this larger space, you'll get a new trace formula that relates the multiplicities of representations to the lengths and holonomies of closed geodesics. Okay, so I'm going to show you a trace formula that I explicated, but I wanted to first show you a non-spherical trace formula from Lin and Lipnowski. The paper was published in 2022, but it was first on the archive a few years ago, and so that's kind of what I modeled some of my explication off of. So in their paper, they come up with this trace formula where on one side they're sampling eigenvalues of the Hodge Laplacian for coexact 1 forms, and also the Betti number of the manifold. So that's our spectral information. And then on the other side, we're sampling both the lengths and the holonomies of closed geodesics. So this is giving us more information than the classical Selberg's trace formula. We're now specializing to a different type of spectrum. Okay. Okay, so what spectral decomposition is this coming from? Well, we're looking at our space, which is the L2 space of PSL2C mod gamma. And we're looking at square integrable functions in this space. And DG is the Haar measure on PSL2C. And under the right regular representation of G on this L2 space, we get this decomposition into irreducible unitary representations of G. And for a co-compact manifold, there will be countably many multiplicities that have that are non-zero. So countably many representations will appear in this decomposition. Okay. Unfortunately, these representations, which I'm writing as pi sub nu p, are completely classified. Okay, so these representations are induced by a character on the upper triangular group, and they're either trivial, principal series, or complementary series. And they have two parameters. Nu is our spectral parameter, and then p is our integer parameter. Okay, but the thing we're going to carry forward is the multiplicities of these representations. So that's what will appear in the trace formula. Okay, so this is a non-spherical trace formula that I explicated in my master's thesis. And what this says is that we can specialize to a particular integer n. Here I'm just showing non-negative for simplicity. And we can sample only those representations with that integer parameter. So we're sampling the spectral parameters on one side with the Fourier transform. And then on this other side, we're now sampling the lengths and holonomies of closed geodesics. So for Lin and Lipnowski, they had this formula for n equals 1. And now we have this for any integer n. Okay. Okay, so it's this geometric term that I want to use to count geodesics. And now I'm going to move into some of the proof behind my results on bias in the distribution of holonomy. Okay, so we'll recall from the first talk that I was interested in looking at this, this bias count, where I'm sampling holonomy with a smooth function f that averages to 0. And then we're looking at this sum that's measuring whether holonomy prefers to be towards those positive parts of that function or more towards those negative parts. Oops, sorry. There we go. Okay. So, okay, and then we're sampling the length with a smooth function, gy eta, that approximates a sharp cutoff at length y, but has an ambiguous region from y minus eta to y plus eta. Okay, so what we can do is we want to use the trace formula to understand the sum. So what I do is I choose the function g tilde, which is basically this smooth cutoff function, but multiplied by an exponential function. And the reason is, the hope is that the exponential will cancel with this exponentially decaying weight. It's not quite that simple because the weight W of gamma is a little bit more complicated. But that is kind of the moral, although you do pick up some terms from that transfer. But the idea is that the geometric term will approximate this bias count. Okay, so then I can use the trace formula to approximate this sum with the other side of the trace formula, which gives me these spectral terms that have to do with the multiplicities of representations. And since P is non-zero, I'm using nu equals IS, where nu is my spectral parameter, but here S is always going to be a real number. Okay. So, okay, and then I can look at what shows up in these spectral terms. And I can see that there's a bunch of e to the y's that appears. And so I'm just going to normalize by dividing everything by e to the y. Okay. And what we're left with are these spectral terms where the only dependence on y is e to the isy, which is just going in a circle. It's not tending more in the positive or negative direction. And then we have our bias constant. And so the idea is that on average, the bias constant will control where this sum is centered. Okay. So I want to show you how I deal with these spectral terms. So what I do is I approximate this by looking at a finite spectral cutoff, where we only have finitely many spectral terms. And the idea is we have these e to the isys, and so we're going to use something called the Kronecker-Weil theorem. Okay, so I want to talk about two cases. So the first is if the spectral parameters are linearly dependent. So for example, if you just have two spectral parameters that are linearly dependent, then the idea is that e to the isy will be periodic in y. So for example, if you have 1/3 and 3/2, then the set spanned by the spectral parameters is just going to be this subtorus that wraps around. So this is a one-dimensional subtorus, but eventually it gets back to where it started. So the idea is if we can have a function of these two exponential functions where S1 and S2 are linearly dependent, we can approximate that by instead sampling over this subtorus. Okay. However, if S1 through Sn are linearly independent, then a function of e to the isy from S1 to Sn are not periodic in y. So they're not going to repeat themselves. And we can see this really nicely through a visual. So here are two numbers that are not linearly independent over the rationals. And so if I look at the set spanned by the spectral parameters, and I look at y larger and larger, you can see visually that this is not wrapping back around to itself. And the closure of this set is actually the entire torus. So the idea with Kronecker-Weil theorem is instead of looking at this as a function of these exponentials, we can instead sample over that torus. Okay, so this gives me this lemma where if I'm sampling my sum with a function h and averaging, that's going to be the same as sampling the space A, which is the closure of the spectral parameters. Okay. But the idea here is that we now have that this ET is distributed according to some probability distribution. And that makes things really nice. Especially if the closure of these spectral parameters is a torus rather than a subtorus. Okay, so why is this nice? Well, if we have that the closure of the spectral parameters is a torus, then it is more straightforward to compute the Fourier transform of our probability measure. So you don't have to worry about the details, but the idea is that we can then integrate just from 0 to 1 in each variable, and everything works out much more nicely. So this Fourier transform can be computed explicitly, and then we can use Fourier inversion to recover the probability measure. Okay, so this is how I get that an explicit formula for the distribution of my normalized bias count and symmetry around the bias constant. Okay, so hopefully that gives you a little bit of an idea of why spectral parameters are involved and why there's a nicer result when you have linear independence. Okay, so I do want to add a word of caution, which is that spectral parameters are not necessarily linearly independent. So in my dissertation, and you can also see in my paper on the archive, I construct an example of dihedral representations that have an arithmetic progression of spectral parameters. So this hypothesis is not always met, but it's reasonable to expect that outside of these really special representations that only occur in certain arithmetic manifolds, in general, spectral parameters we expect to be distributed pretty randomly. So in general, it is reasonable at least to expect linear independence. Okay, so I'll stop there. Thank you so much for listening. Please let me know if you have any questions in the Discord or at office hours. And these are the references that I used for this second talk, if you're interested in learning more. All right, thank you.